So in the radical halogenation introduction video, I illustrated the radical halogenation mechanism by showing the mechanism for radical chlorination of methane. In later videos, we saw some chlorination reactions of other alkanes. In this video series, which this is the first video, we'll be looking at the general mechanism for radical halogenation, as well as the energetics involved in the process. So that's that's reactions of any alkane with any halogen. And looking at the thermodynamics of the process, remember thermodynamics, energetics are interchangeable terms. Looking at the thermodynamics of the process will give us some insight into why certain halogens more readily react with alkanes to furnish haloalkanes than do others. So the general initiation step is you have the halogen is basically denoted by an X. You have homolytic cleavage to form two halogen radicals. This is, I shouldn't say step one, I guess I should say this is the initiation step. Initiation, hopefully you can read that. Then this is propagation step one. So in propagation step one of the halogen radicals reacts with an alkane that I'm going to just denote RH. R is a generic term for an alkyl group. This is just an alkyl group, and that's basically the alkane minus the hydrogen, without the hydrogen. So this alkane homolytically cleaves. This bond undergoes this bond between the alkyl group and the hydrogen homolytically cleaves, and oops, it should be a half arrow here. Okay. So this halogen radical joins with the hydrogen. Get a hydrogen halide and an alkyl radical. Just draw that as an R with a dot. And then you have propagation step 2, which involves the alkyl radical generated in propagation step 1 reacting with the diatomic halide, the diatomic halogen. So that halogen undergoes homolytic cleavage and bonds to this alkyl group, and you get the haloalkane alongside the halogen radical. And what you'll immediately notice here is that the radicals furnished in propagation steps 1 and 2 are each used in the other propagation steps. So this halogen radical furnished in propagation step 2 is used in propagation step 1, and the alkyl radical furnished in propagation step 1 is used in propagation step 2. So this process continues until one of your chain termination steps occurs. And we went over this in the case of chlorination of methane, but in general, one of these three combining of radicals will result in an ending of the propagation steps of radical halogenation. So we could have two alkyl radicals generated in propagation step 1. They could combine to form this alkane. So say the alkane that initially was starting was say it was like ethane, for example, right? The ethyl radical will look like this, and if you have two of them, you know, let's say you have another one, they'll combine and you'll get butane, right? And this is just what R bonded to R means. So that's one possibility. Another possibility is you have a halogen radical combining with another halogen radical. So you'll get that, and that this is equivalent to X2. It's just another way of writing it, showing the sigma bond between the halogens. Alternatively, you could actually have the alkyl radical combine with the halogen radical, excuse me. And that's really that generates your product, but it also can serve as a termination point for this reaction. If one of these three things occurs, then the reaction can terminate and the process would end. But remember that the first step of the reaction involves hydrogen abstraction. The likelihood of a particular hydrogen being abstracted is governed by the stability of the radical that forms upon hydrogen abstraction. So when we look at, let's say our starting alkane was 2-methylbutane. Let's say we're 2-methylbutane. So the radicals that are or the hydrogens that are least likely to be abstracted are ones that would result in primary alkyl radicals, and those would be hydrogens on this carbon. So any of these hydrogens here, these here, and these on this carbon, right? So notice these carbon atoms are only attached to one other carbon atom. This one's only attached to this one. This one's only attached to this one. This one's only attached to this one. So these are the least likely to be abstracted. This one, these two hydrogens on this carbon are a bit more likely to be abstracted. So let me put here least likely. And these are a bit more likely to be abstracted. These hydrogens on this carbon is a secondary carbon, so that makes these hydrogens secondary hydrogens. That's because a carbon is bound to two other carbon atoms. So these are more likely. And this hydrogen is actually the most likely to be abstracted, because this carbon is bound to three other carbon atoms. So I'm going to say this is the most likely. And of course, the product distribution is actually also dependent on the number of hydrogens at each position. So at these are equivalent. These are primary hydrogens. So each one is among the least likely to be abstracted. But there are 6 of these. These are also primary hydrogens, but they're an additional carbon away from this branch point. So these are not equivalent in energy to these. So these are not equivalent hydrogens, although they're primary. But you have to take into account the number of hydrogens as in each position, as well in tandem with the likelihood of abstraction of any given hydrogen, to give you an idea of the percentage of any particular product that's going to be formed. But remember that it's the halogen radical that actually does the abstracting. So if you go to the propagation steps here. Propagation step 1, you can see that the halogen radical is the atom or molecule, well, I guess it's really both at this point, that abstracts the hydrogen and results in the alkyl radical. So it's the halogen atom that does the abstracting. What happens if we change the halogen used in the reaction? We so far only dealt with chlorine as the halogen, but what if we were to use, say, fluorine or bromine or iodine? Well, this is what we're going to take a look at in the next video.